By the way, our presentation at the moment is on equation of motion and optimization. But unfortunately, I don't think I'm going to have enough time to go in detail in this. I'm going to revise some certain things with you, then then I can give you some exercises you can do to use those things which you have revised. First of all, let's start with this kind of situation. Let's suppose we've got a graph on the system of axis XY coordinate. Something like this. When you've got a graph like this, let's say this is y is equal to f of x. If you already have done differentiation, I want you to be able to talk about these graphs in terms of derivatives. Altogether, I think if we have got that point there, I think if you say x there, whatever x is there, we can say at that x there's a turning point there. In other words, the function was increasing here, and now it's decreasing there. So there is a turning point. Similarly, there is a turning point somewhere here. But a turning point, if you draw a tangent line, you must know that the tangent line is parallel to the x-axis. And then its gradient, in this case at that point, which is dy dx, evaluated, let me call this point x0 here, and I call this one x1. So its derivative evaluated at x equals to x1, in this case, must be equals to 0. And when the gradient of the line is 0, we know that the line is horizontal. So similarly, something will happen here. If we draw a tangent there, it will exactly give us the same thing, that dy dx, first derivative, at x equals to x0. When we call a point x0 or x1, in most cases, is a point which we know, a particular point altogether. Then x is just a general point which we haven't fixed as such. So this is also going to be at 0. Now, if we value that derivative somewhere here, there, you must know that the derivative dy dx, if you value it at any point somewhere there, dy dx will be greater than 0. That will be pointing at the fact that the function is increasing. Now, if I take a function, doesn't matter whether it's something like a cost function for a certain production. If I differentiate that cost function and I evaluate it at a certain time, I find it that the cost function there, the derivative is greater than 0, which means that the cost of production there is increasing. But on the other side, if I evaluate somewhere here, you will see that dy dx there will be something less than 0, and then it shows that the function is decreasing. And when the function is decreasing, like if I was just talking about cost function, if the cost function is decreasing, it means that you're actually making more profit because you are producing at less cost. Is that right? So those are the interpretations you must have when you go to all these things. Similarly, you can check something there and there. Okay, this discussion leads us to this kind of a summary. This is this kind of a summary. If we were to optimize a function, in other words, when you talk about optimizing a function, we are talking about finding points where the function is either maximum or minimum. Any businessman would like to operate with a function, cost function, which is at its minimum, so that the profits go to its maximum altogether. That's how that thing runs. So when we talk about optimization, we talk about such a thing. So we need the derivative. In this case, to decide whether it's maximum or minimum, we have to calculate the value of the second derivative at that point. Now it says, if the value of the second derivative is less than 0, it means that we've got a maximum at that point x is equal to a. And if that derivative is greater than 0, it means that there's a maximum. But there are situations whereby you find that the second derivative is actually 0. Then these two criteria there cannot be used to decide. Then what do? You have got to resort to other type of investigation. One of the easiest type of investigation you can do is this one. Let's come back here. let's say this second derivative of this function there was 0, and I didn't know whether there was a maximum or a minimum there. What I can do is I can evaluate the first derivative on the right of the turning point, on the left of the turning point, and evaluate the derivative on the right of the turning point. That is, I can say here x0 plus, on the right, and evaluate their way at x0 minus, on the left. If the sign of that derivative changes, look, from positive to negative, it means that the function was increasing, then suddenly it decreasing. I think you must have a feel that there must be something which is a local maxima altogether. You understand what I'm saying? But if you come this side, on this side, and you take a point here, which is on the right of x1, and or on the left of x1, and evaluate the first derivative. The first derivative is going to give you something like this, the tangent will be like this. And this side, it will be like this, which means it's increasing. So if it was decreasing, then suddenly it goes up, which means at that turning point, there must be a minimum altogether. That is what you can use when the test of second derivative fails, when you don't get those two inequalities. If you fail to get this inequality, and they fail to get this inequality, and you get this one, then you can use to that testing of the first derivative on the left and on the right. All together, guys. Okay, be careful. You must listen very, very careful and make sure you understand. Then, there is an example. In other words, here, what we've got here is we've got a car moving, and meters, S is distance in meters, and the T is time in second, and that is that. If you look at this, this problem is a problem of what? Of motion. Then let's come to this. What you must know, when you're talking about linear motion, you must always know that the function displacement is represented by S. We write it there as S, a function of T. Obvious, when you move from home to school, you move a distance which you cover in terms of the time which you have used, isn't it? The less time you've traveled, maybe the less distance you've gone. Altogether. Okay. So that is that. So then we've got velocity. What is velocity? Velocity is actually the rate of change of distance over the rate of change of time. Altogether. So then you get that as distance as a velocity, and in this case you measure it as meters per second. Altogether. But remember, velocity is normally a vector, but here what we're talking about is velocity, which is fine, is actually what we call speed, if we are to be strictly correct. Altogether. But we can continue to call it velocity, there is fine. But then if you now continue and look at the rate of change of the velocity, now as you say dv dt, that will be the d second of s d, that this is going to give you what we call acceleration. Altogether, like you saw my heading there was saying optimization and motion. So I'm going to give you two examples there. One which deals with optimization and the other one deals with motion. So the first example here actually deals with equation of motion. So there is our S. What is this? What are we asked to determine? We are asked to determine the velocity. Now let's write here solution. So since we are asked to first velocity, we first of all need the expression of the function v of t, the function velocity as a function of time. So what we do, we say that is ds dt. Then that is going to give us differentiation of that. We did revise differentiation. I think you can see they are going to use the power rule throughout. Is that right? So I'm going to be quick on that one. Who can give me the first derivative? What's the first derivative? There? 90 squared. The next one, minus 4t. The last one, no, the next one, plus 4. The last one, plus 0. I'm not going to write it. Please leave that function there. You are asked for to determine this velocity where at t equal to 0 and at that time. So now we're going to say v at 0. This is ds dt for t equals to 0. Do you see that? Don't disturb this function because you're going to use it several times. Leave it there as it is. Then you say equals 9 0 squared minus 4 times 0. I'm using brackets there because I don't want that to look like 40 or 90 squared. So 4 times 0 plus 4. What I'm going to get here are meters per second. Meters per second are the standard international units for measuring velocity. SI units, standard international units. Okay, so that will give us 4 meters per second. Be careful when you answer these problems. If you don't give units, you might be penalized for not giving units. So please always give your units altogether. Okay. Now the next thing is velocity at that. Then I'll say velocity at 1,5. And this one, I'll ask you to do it yourself. DIY. Altogether. Okay. Let's proceed to acceleration. If you now we need acceleration, we need this function. That's why I said you must leave that function standing alone there very clearly. We need that function. So what we're going to do? We're going to say A as a function of t, just like the A of t, equals to d second of s dt, which is actually the first derivative of v with respect to t. Then I differentiate again here. I think it's clear that that is 18t minus 4. Are we there, guys? Okay, minus 4. Then, if we now want A at 0, what are we going to do? We're going to say dv dt at t equals to 0. Then we substitute by 0 there, we get 18 times 0 minus 4, and then we get this equals to minus 4, and the units here are meters per second squared. The squared comes from there. Altogether. Okay, so this is how we do it. Now this acceleration is negative. What is happening to this particle which is moving? What is happening? Is what? The speed is increasing. What's happening? It's slowing down, is it? So those interpretations must be present when you are dealing with these things. Are we together? Okay. So that's an example on motion, and I hope it's good enough for you to be able to repeat several other examples. So in addition to this was linear motion. You should remember also that there's angular motion, where things are rotating. Are we together? Then on top of angular velocity, you top of angular acceleration and so on and so forth. But the working is exactly similar. Now let's come to this example. In this case here, we have an example which is for angular motion, but I think I'm going to leave this one for you to do it. Are we together? So, solution there, I'll say that do it yourself. There is Listen, I think you understand. I'm running short of time now. I need to look at the example for optimization. Altogether. But if you later got problems with that, it doesn't mean that if I say do it yourself and you cannot go, you cannot manage to get it, you must still come and ask. Altogether, guys. So I'm not like abandoning you there. Okay. This is the summary of what we had before for linear motion. In this case, we've got it for angular velocity. I think that's the end of our discussion as far as what linear motion is concerned. Let's come briefly discuss what we call optimization. Optimization. So now guys, listen here. It's the same thing. I think I've said this thing again and again. When you optimize something, you basically you are dealing with a certain function, but you want this function to operate at its optimal point. Basically, optimal point in this case, it depends on what is convenient for you. If you want to maximize profit, I think then you must run the cost function at its minimum and the profit function at its maximum. So you say that my profit there is optimal. But let's look at a situation, simple situation like this. Let's suppose, I'm just trying to give you an idea of how you could come up with a function in a situation given. Let's suppose I've got a river here. A river normally is not a straight line, it's something which meanders like that. And suppose I've got maybe 1,000, that's about a kilometer of net wire, which I can use to fence a rectangular kind of something like this, more or less. But we can assume roughly that these two sides are equal. Maybe, let's say, let me just adjust my river. Let's just say the river meandered there and it came here, and this side here is equal to this one. I just want to make the problem less complicated. So assume that these points there, they're almost at a certain level. Otherwise, if I make a dot there, that will be what? A rectangle. Now somebody says, okay, if we're going to keep sheep here, you know what kind of animals are sheep? If this stream is always having water, this sheep is not going to cross. So there's no need to put a fence here. The sheep are just going to come to here and drink and go back to the paddock. Altogether. So I've got only 1,000 meters to do this thing. So somebody must say, okay, in order to get the maximum area, what am I doing? I'm optimizing the area. In order to get the maximum area with my 1,000 meters of netted fence, to fence this, what should be the dimensions x and the y? What should be the length and the width of this thing? So what do I have there? I've got a function which is called function area, which is x times y. So this function will change, depends on what I choose to be my x and y. Somebody might do this something very fun, very, very fun. Somebody might try to take 900 meters of this, let's say 98 meters of this, and they put it like this. And they call this, and they call that. So you put 98 here, 1 meter there, 1 meter there. Which means the sheep are going to live here only 1 meter away from the water. And when the water is running, these sheep are going to be traumatized because the noise of water is frightening them. Altogether, that will be the most, I don't know what. This will be done with somebody who's got rocks in his head. Rocks, I really mean rocks. Altogether. So you can decide on dimensions in such a way that the sheep are reasonable, away from water, can graze peacefully without being disturbed by water and all those things. So now we have to choose this nicely. Now if we want to choose this nicely, if we wanted this function to depend on x, to be a function of x, I think you can guess that now y must be equals to 1000 minus x. Do you agree with me? Yes or no? I've got 1000 meters, I've decided the width to be x, then because I want my function to depend on x, then y must be 1000 minus x. Do you agree with me? So which means here this function is equals to x brackets 1000 minus x and equals to 1000 x minus x squared. Who knows this kind of a function? Who knows this kind of a function? Nobody. Nobody. To me it looks like a parabola. And the parabola which is cut down. And the parabola which is cut down is normally looking like this. Because I don't know the line of symmetry, it's normally looking like this. And the parabola which is cut down can only have a maximum. Do you understand what I'm saying? A parabola which is cut up down can always have a maximum. So now let's search where is the maximum. For what value of x is this maximum? So what do you do? dA dx. So this is a different dA, ne? Equals to 1000 minus 2x. So I want to see where this is going to be 0. Then we say 1000 minus 2x equals to 0. We solve this, get minus 2x equals to minus 1000 x. We say our x is equal to 500, about half a kilometer, 500 meters. Now, we know that at 500 there's a turning point, but we don't know whether it's maximum or minimum. So what are we going to do now? We now need to do the second derivative. Check, I left my first derivative there clean. Then the second derivative, what is it going to be? Minus 2x. Do you agree with me? Okay? Sorry? Minus 2x? Minus 2. Somebody agrees with me there. I saw somebody agreeing with me there. Minus 2. Now this function is a constant function. It's minus 2. Whether we value it at 500, whether we value it where, it's always going to be less than 0. But we saw the message before that the message is whenever the second derivative is negative, it means the function is got maximum. So this function is got maximum. The area A is going to be maximum. Now if they say find that area which is maximum, find it, what are you going to do? You come back here, you know x is 500, then that is what? X minus 500, then what is this? This is 1000 minus 500, and then this is what? 500. Oh, which means this is going to be look more or less like a square. Altogether. So then the area then will be 500 times 500. I think you can see how many square meters is that. So simply what it's suggesting to us is that if you've got a certain amount of fence to do, and you want to cover the maximum area, I think the best thing is to try to make it a square. Altogether, you saw here making a kind of a deformed triangle like this one, giving 1 meter there, 1 meter there, actually will give you minimum area because it's going to be 1 meter here, 1 meter there, 900 meters there. Then you multiply, sorry, 800 meters there. When you no, not 900. 1 meter there, 1 meter there. What's going to be there? 1000 minus 2, it should be 900 and something. And then when you multiply that 1 meter with this 9 and something, you only get 900 meters squared. And the inconvenience is small, and secondly, your animals are living next to the water, which is going to traumatize them, and that's very bad. Altogether, up to that point, I think I've done what I was supposed to do, and I would like to say thank you for listening. My name is Charles Wasfani Msipa.